Okay, so both of them are minimizing the output size, but one also takes into account the right-hand side, the Q, the certificate, and the other does not. So that makes a difference, a small difference there. This one minimizes the sum R plus D, order plus degree. That's interesting to minimize if, well, not in this case. If you are doing integration here, so with x and y, then you get some power series here, and you want to get a recurrence for the power series coefficient. Then if you have a differential equation here of order r and degree d, then this translates into a recurrence of order r plus d, which you want to minimize there, at degree r, right? That's this. That's the one that we discussed, this also. And this here is the one which minimizes the computational complexity. So this is when you figure out what is in the end, in order to compute this creative telescoping relation, what do you really have to solve? You have to solve a linear system of equations that still involve the parameter n or x, depending on whether you do integration or summation, and you have to solve that. So you have to figure out how big is the system, what are the degrees in the matrix, and then you do the same as here, you plug this in and minimize this, and you find that the minimum cost is not where the minimum order is. And that's something that's not clear a priori. But it's also not such a spectacular effect because it's very close. So in all, oh yes, and I should say because it's recorded, we are not the first who observed that. So the French group has done such an analysis on a slightly different context, and they have first observed that making the order bigger can cause a degree drop, which is so much more than the increase of the order that it pays off asymptotically. So what we have done is we have applied it to this case, and we have computed explicitly this curve, which they have. They have just said something here is not as good as something here. Okay, so now that picture is a bit idealistic because in real examples that you really can compute with today's computers and so, they are in fact identical. So they are very close. The minimum cost and the minimum order are very close. So that everything that you can compute with Maple and so, there will be no difference. But in 5 years, there will be a difference. Because somehow we have considered a hypothetical example in our paper where we predict the blue curve. We can do that because that's easy. And then see, okay, if the example is about twice as big as we can currently compute, then the minimum order is 7 and the cheapest order is 8. Okay, then you say, okay, maybe that's still not very convincing. But it becomes more and more as the example, as the input becomes bigger. So in the end,
in 500 years, will be substantial.
Yeah, asymptotically it's substantial. You can make this precise. So if you say, okay, let's see if I remember this. Well, I'm afraid I don't remember this. So let's say tau is some quantity that measures the size of the input in a way that I don't want to explain because it doesn't matter anyway. Then we can say what is the cost? What is the cost for computing this one? And what is the cost for computing this one? As tau goes to infinity. And then we find this. So minimum order has a computational cost. Oh, do you know what is the complexity of Zeilberger algorithm? Yeah. I tell you, it's tau to the 9. Okay, so that's a bit scary, but at least it's polynomial. So it's polynomial time complexity. That's not obvious, but it's a fact. And that's if you go for the minimum order, the one that is most expensive. If you go for, and no, not O of, we know it more precisely, and it was a lot of work to make it more precisely. It's 2 times tau to the 9 plus O of tau to the 9. Okay. And then if you go for minimum cost, then it's tau to the 8 plus O of tau to the 7, where there is some funny constant here, which I'll tell you in a minute. 359 plus 8, 5 square root of 17 over 32. So this is the best constant that, and don't ask me what is the approximate value of this. Yeah. Well, anyway, so that's a number that we can compute explicitly. And then the question, which is also interesting here, is, so let's say this is order R min that you get, minimal order. And now what is the order for which you achieve minimal cost if the example is very big? And asymptotically, it turns out that the minimal cost is when you take, so that's R min. So now this I can tell you what it is. This is approximately 1.28. So what this says is that this one will move to the right, and they will become that they will get some distance as the example goes to infinity, but not much, just 30% more. So if you have a big plate telescopic problem, then the advice following from this analysis would be to choose the order about 30% higher than the minimal order. That will be the cheapest way to compute the relation. There's some time left.
Yeah.
So I'm
The meaning of minimal cost is such that it means also minimal complexity.
Yeah. A minimal complexity, what we count is operations in the ground field. If the ground field is rational numbers, then this is not very adequate, but that's the best that we can get.
But Manuel, this is beautiful analysis. From a practical point of view, it all boils down to solving a system of linear equations with symbolic coefficients. So you can always plug in random values of n, and thus empirically find out what's faster. Will it indicate?
No, because you have to know, if you plug in something, then you get only the solution space with something plugged in. So you don't know what is the degree of the solution when you lift afterwards. So you can say, you find here a solution, and then you do lifting, Chinese remaindering, interpolation, and here you will find a solution. If you do it here, you have to go up to here. This changes the complexity. And if you don't know this analysis, then you don't know how high you will go. So this analysis is possible because we know how many evaluation points.
We know the curve a priori.
Yeah. Yeah.
So this is a lower bound. Is this a lower bound for the complexity?
No. This is not a lower bound. It's an upper bound.
I see.
It's an
So
upper.
is it known? Is the lower bound known?
No, I don't think so. No. Well, there's a. You can think of a lower bound because you know you can estimate the size of the output, and the complexity has to be as
Right.
big as the output. But I don't think
Yeah,
you
you have
can.
triple lower bounds. But lower bounds are very hard usually.
You cannot estimate the output size from below. You can only estimate it from above. And so that's because it can be always sparse, as
Sure.
I said before. And then, how do you see this before?
Okay.
Okay, and the other thing is that I have to say that we don't know the blue curve exactly. So we know only some sort of approximation. So if this is the blue area, then we know our blue curve is something which is inside. So that, and typically it's somehow, we have examples where it's very good, but it's not always very good. So there are examples where it's somehow, where there's a gap. And there, somehow, that for this reason it's just an upper bound. It can be that you find something before. And it can then also be, because we don't know exactly whether our bound is tight, that this is not the best thing really, but it's the best thing according to our analysis. Okay, so what I could do is to fill in this. So I wrote here d greater something r plus something divided by something r plus something. I could tell you what these somethings are, but only if you insist.
Maybe just one something? Is it rational?
Yeah. Of course, they depend on the input. So for a specific input, it's a number. But the formula is quite a mess. Okay, so I can start to write it down, and when you are tired, you tell me. I'll write it down for integration, because we haven't finished the summation case yet. Okay, so integration. So we have integration h x y dy, where h is a hyper-exponential term. So what is this h? Is something that looks like this. It has c0, that's a polynomial, times e to the a over b times the product L from 1 to L, C, L, e to the L. Okay, so the a, b, and the ci's are polynomials in x and y. And the e's are some coefficients, so some exponents that need not be integers. Okay. And then, so let's say that the degree of A is, so there's a case distinction. The degree of A greater than the degree of B or not. Let's take only one case, just for illustration. Suppose the degree of A is greater than the degree of B. Then the formula looks like this. It says D is greater than alpha plus beta 2 gamma minus 1 plus phi 3 plus gamma minus 1 r plus lambda divided by, so here's the r, divided by r minus gamma plus 2 minus phi 3. Okay, I have to tell you what alpha, beta, gamma, phi 3 and lambda are. So let's start with lambda. Lambda is the degree of C0, this one here, in x plus alpha plus beta plus 1 times the degree of the C0 in y plus gamma minus 2 plus phi 3 times the degree of C0 in x minus alpha minus beta minus phi 2 minus 1 minus phi 2 gamma minus 2 plus phi 3, the maximum of this and 0, times phi 1 plus 1/2 beta, where I'm lost, gamma minus 1 plus phi 3, but it's all relevant for the exam. Okay, so this is this. I still have to tell you what the alpha, the beta, and the gamma is, and the phi 1 and the phi 2 and the phi 3. I continue here, if this is visible.
Did you derive this formula by hand or by computer?
Good question.
I hope not by hand.
No, I had a Chinese collaborator. No, we derived it by hand, but we checked it with the computer.
Not good enough.
Simple.
Okay, so alpha, beta, gamma, delta. In fact, that I should mention that this is the easy case. Because in the other case, there's also delta and omega. There's no delta and omega. So just alpha is the degree of the square free part of b in x plus the degree in x of b itself plus the sum over the L's of the degrees in x of Cn. Beta is the degree of A in x minus the degree of B in x minus 1. And gamma is the degree in y of the square free part of B plus max degree by A degree by B oh, okay, this can be simplified in this case. This is just the degree of A. No, it cannot, because this is degree in X. Or if you can go if you want. Degree Y B plus the sum of the L's of the degrees and Y of the CL. So this is alpha, beta, and gamma. Now the phi's. Okay, so phi 1 is, so these are flags which are either 1 or 2. So this is 1 if the leading coefficient of A divided by the leading coefficient of B is in the ground field. So remember that A and B are polynomials in X and Y. So if you take the leading coefficient with respect to X, then this is usually a polynomial in Y, and this also. But if they are just a constant multiple of each other, then this is 1, and otherwise it's 0. And the phi 2 is the same, phi 1 times, and then you check whether beta is 0. So it's 1 if beta is 0, and 0 else. Okay, and now the last final thing, phi 3 is 1 if, now that's a bit a technical thing, so if the degree in Y of A, the degree of Y in B is equal to 0, and for all the L's here, we have either that the degree of CL in Y equal to 0, or the BL, this exponent here, is in Z, so an integer, and degree in Y of C0 plus the sum of the degrees CL is greater than -1, and 0 otherwise. Did I make a typo somewhere?
Yes.
Where?
Yeah. Very good. Time is up.
48 minutes.
Thank you very much. Manuel will be glad to answer questions in private. Thank you. Also, we're taking Manuel for dinner.